Welcome. This question says 4 kilogram minus 10 degrees C block of ice. So let's imagine it. This is 4 kilogram minus 10 degrees C block of ice is dropped into a calorimeter. So here's my calorimeter. And that contains 8 kilograms at 20 degrees C water, and showed that the equilibrium temperature of the result is 11.4 degrees C. It drops in and melts. So I've got to visualize this a little bit. And this is this up here is temperature, and this here is energy, Q. Let's draw the characteristic for water and ice. Let's draw this. I'm going to erase this to give myself a bit more space in a minute, but just to remind ourselves, so this is the solid, and this is solid melting to liquid, this is a liquid, and then this is liquid becoming vapor. And what's happening here is we start off, let's do a different pen, we start off with the ice cube, and the ice cube is lower than its melting point, which is 0 degrees C. So we start off here, and we raise the temperature by putting heat in, and then we melt it by putting heat in, and then we have some heat left over which raises its temperature to its final temperature, TF. And this is paid for by the loss of energy, if you like, the transfer of energy. This is T hot of the hot water, and as that hot water cools, so we give Q, and the amount of energy that we need is equal to the amount of energy given by the hot water. If we give a little bit less heat, then we'll have a lower temperature. If we give a bit more heat, we'll have a higher temperature. So we're trying to find this equilibrium temperature, this T final, and it is going to be the temperature at which the various mechanisms of heat gain by the cold object balance the mechanism of heat loss by the hot object. And because it's ice and water, we can draw it all on this same diagram. What this tells me is that I have one step which is heating up the ice to its melting temperature, another step which is melting the ice, a third step which is heating the melted ice, which is now ice water, to its final temperature, and a fourth step which is the giving of the energy by the hot object. 4 terms, and so my equation has to have 4 terms in it. I didn't draw that diagram particularly well, but hopefully you got that idea across to you. And so what I'm going to say is, I'm going to say that the sum of the Q's equals 0, so Q gain plus Q lost equals 0. And for the Q gained, I have, well, the heating of the ice. So we have the mass of the ice times specific heat of ice times the temperature change for the ice. And then I'm going to add to that, now I've got to melt the ice. So it's the mass of the ice times the latent heat for ice. And now I've got to heat up the melted ice water. It's still the same mass, so it's still the mass of the ice, but now it's water. So it's the specific heat of water times the temperature change for the ice water. And then I've got to add on to that, well, the mass of the hot water times specific heat for water times the temperature change for the hot water. and all of that equals 0. So 4 terms. I warm the ice to its melting temperature, I melt the ice, I heat the melted ice to its final temperature, and all of that is paid for by a cooling of the hot water. So if I look at these numbers, then I have 4 kilograms of ice, and the specific heat of ice, it's not really ice, that's why it's in inverted commas. You know, in my pretend ice, my specific heat is 2 joules per kilogram per degree C, just to make the numbers simpler. And then here's a conceptual bit. The melting point of ice is 0 degrees C, and I start at -10. So my T final is 0 minus my T initial is -10. Common mistake is people put down T final here because they're not recognizing they go in steps. So this is the mass, this is the specific heat, and this is the temperature change. Final minus initial. And then I have the mass of the ice, because now I've got to melt it, it's 4. And then I've got to look up and say, what is my latent heat for ice? And again, I'm kind of cheating. My latent heat for ice is going to be, I give you the latent heat for crystallization and the latent heat for vaporization, and we're melting ice, so it's down here. So that's the 6. 6 joules for every kilogram. Again, that's not the real number. It's just to keep the math simple. Now, although it's melted, it's still the same amount of stuff. So again, I have 4 kilograms of, now it's water, but it was ice. Because it's water, I use the specific heat for water, which is 5 kilograms, joules per kilogram per degree C. Again, not the real number, but just a simplified number. And now I have my temperature change for this melted ice water. Well, its final temperature is the final temperature in the experiment, and its initial temperature is the melting point of ice, which is 0. I have a 4th term, and this 4th term is going to be the mass of the hot water, and that's 8 kilograms. And it is water, so I need the specific heat of water, which is 5 joules per kilogram per degree C. And now I've got to do its temperature change. And yes, it ends at T final, but it started off at 20 degrees C. Not that hot, but that all equals 0. Now, just stop for a minute. TF is less than 20. So, because this is cooling down. So that's going to be a negative number. And TF is more than 0, so that's going to be a positive number, minus, positive number. So I have 3 positive numbers which balance out this negative number to equal 0. So this is going to be 8 times 0 is 0, plus 8 times minus 8 times plus 10 is 80, plus positive 24, plus 5 4s are 20, 20 TF, and while we're at it, let's put down 20 times 0, doesn't matter, minus 0, positive 0, makes no difference about that sign, and then 40 TF, and then minus, plus, minus 40 times minus 20 is minus 800. So then this is 80 plus 24 plus 20 TF plus 40 TF minus 800 equals 0. And now we're doing math. This is going to be 60 TF is going to equal That goes to the other side and becomes positive 800. This is 104. So this is going to be minus 104. So this is going to be 694 TF. And there's going to be 694 over 60, which equals, that goes in that once, 1, 5, 30, sorry, I'm doing it in my head and I shouldn't do it in my head. It goes into 1, 6 goes into 9, 1 carry 3, 6 goes into 34, 5 times carry 4, 6 goes into 40 6 times, and that's going to be 11.56 degrees C. I said 11.4 degrees C. I'm a little bit out on my calculation there. I made a slip somewhere and didn't spot it. But this is the right answer. I'm convinced of that. 11.56 degrees C is my answer. Most common mistakes. Most common mistakes are people think that T final is whatever is at the end of my bracket. So rather than recognizing that the final temperature for the heating up of the ice is 0, they'll put T final in there. And then another thing people do is they'll just miss out an entire term because they did not look in any detail at this relationship where we have the heating of the solid ice and we have the melting of the ice, and then we heat the heating up of the melted ice water, and all of that is paid for by the cooling of the hot water. So there's 3 terms requiring temperature and there's 1 term giving temperature, and that's 4 terms altogether. So there we have it.